All right, good afternoon. Happy Friday. I want to remind you, coming up very quickly is our first exam, so a week from today is our first exam. It will cover the material that we get through on Monday's class. So whatever we do on next week, Wednesday, won't be on this particular exam, will be on the next exam. But just to give you some stopping point for what you need to study for the exam. So up through Monday's class. Let's see. Supplemental instruction. If you're going to supplemental instruction, on Monday there won't be supplemental instruction. Or are you going to do that?
No, I won't be here.
You won't be here. Okay, so there's no SI on Monday. There will be SI on Wednesday. I imagine there will be a lot of students coming to that one. Also, I'm planning to have a review session on Thursday. This room is available from 3:30 to 5:30. I know that probably won't fit with everyone's schedule, but that's the time I can get the room. So I'm going to plan on having a review session on Thursday, so feel free to come to that. And Friday exam. So we'll talk a little bit more about the exam next week. Any questions on that? Okay. Let's talk about conformations. We've been spending this week really looking closely at the structures of molecules and how they actually move, and looking at specific details about the interactions between groups on a molecule as they do their motions, in particular rotations around a single bond. And so recall we talked about the butane conformations, where if you have a carbon-carbon bond and you have differently substituted groups on one end or the other, for example butane, they can be in different positions. So here in this anti position, as you rotate the carbons relative to each other, they can come closer together. There are a lot of terms that you should be familiar with that we've talked about along the way. Anti, dose, staggered, eclipse. If you're still not sure what those terms mean, you should study those. And as we look at a molecule like butane rotating all the way around in 360 degrees, you can see as you go along that different interactions between the molecule provide different amounts of energy to that particular conformation. And they're not always equal. So we talked about this. The lowest energy conformation for butane is this one in which it has an anti-staggered conformation. That's here on the lowest point on this energy graph. As you eclipse the bonds, then we increase what kind of strain energy? What do we call that? When bonds eclipse, we increase the energy of the molecule because of steric strain, yes, but more importantly, torsional strain. Torsional, remember, torsional strain is the electron repulsion between the bond from the back to the bond to the front. Yes, steric strain is involved as you get those larger groups closer to each other, and that's why we go significantly higher in this eclipse conformation relative to this eclipse conformation. Because in this one, we have put both of the methyl groups bumping into each other. So hopefully that reminds you of some of the things we were talking about in terms of butane and the energies associated with the different interactions. So we have steric strain, we have torsional strain involved in molecules. Those particular types of strain energies increase when a molecule has other restricted conformations, in particular when we make green molecules. Okay? That is because we're forcing the molecule into conformations and shapes that aren't freely movable and that alter what the normal energies might be in terms of the angles, for example. So there's extra energy usually imparted to cycloalkanes because of ring strain, which is made up of various combinations of these three things. Torsional strain, steric strain we've talked about, and also the forcing angle, bond angles to be smaller or larger than what they should be according to the best or lowest energy conformation for an sp300 isocarbon. Okay? So I want to continue talking about the conformations of cycloalkanes. In particular, when we get to six-membered rings, there's a lot of detail about how six-membered rings actually move and affect the structure of the six-membered ring. So if you look again at this smallest ring molecule, cyclopropane, it has the highest energy state. This is again a graph which shows the relative energies, actually the extra energy provided by being tied in a ring. So actually the 0 point is the molecule, is the energy of a molecule with that number of carbons that would not be in a ring. Okay? So a 3-carbon ring molecule versus an acyclic propane has increased energy due to forcing the bonds together, angle strain, torsional strain. Okay, and as you get larger and larger rings, this is a 4-membered ring, this is a 5-membered ring, that extra energy due to being in a ring gets smaller. And the lowest point on here actually is a 6-membered ring. 6-membered ring has no extra energy because of the ring, because once you get to a ring size suitably large enough and not forced to have any additional torsional strain fixed in one position, it can adopt a conformation which minimizes all of those things to the best extent. So it's no different than if it were just an acyclic molecule in that open chain form. All right? Okay, cyclopropane. As I mentioned last time, cyclopropane is the smallest possible ring, and because of the very small angle between a carbon-carbon bond in here, being only 60 degrees, it's so small that even the orbitals can't overlap in a linear end-to-end fashion. So if you were to see where the electron density is in the covalent bonds between the carbons, you see that the electron density actually is bent out away from the linear bisection of those two carbons. That's because that angle strain is so high that it can't get to that linear. That would be nearly impossible. Probably is impossible. So the bonds are highly strained in cyclopropane. We talked earlier about reactivity of alkanes and how they're relatively inert, except it's something like burning them. They don't do a lot of other chemistry. However, I will say cyclopropane, because there's a lot of angle strain in this molecule, they tend to be less stable and more reactive for a variety of different reactions. They do a little bit more than most other alkanes because of that. And you can see why. Hopefully this gives you a good visualization of how strained those bonds are. That makes those bonds weaker. So cyclopropane bonds are weaker than a typical carbon-carbon bond in an alkane. Okay? One thing that I didn't really highlight here is that if your angles in the ring become smaller, the other two groups that I haven't written on each of those carbons, those angles tend to open up a little bit, right? So what haven't I written here? I haven't written the hydrogens. Okay, so there's for example, a hydrogen coming up. Oh, it looks good on mine. There's a hydrogen coming up and a hydrogen going down, and actually that angle tends to tends to get wider because these are being pulled closer together. So that does affect the shape of the molecule as well. If you look at this now in a model structure, you can see some of these things a little more acutely. So what I've shown here is basically a stick figure for cyclopropane looking sideways at one of the bonds. This is a space-filling model of that as well. And then I've turned it. And I've turned it because I want to make the analogy to you looking at a Newman projection of one of the CC bonds of this ring. So if you envision this particular bond and you're looking down that bond, this is what you would see here. Okay, so you could represent that like a Newman projection. Oh my God, it's terrible. Sorry about that. Okay, does that make sense? And so that's kind of what we're looking at. Let me just erase that so we'll have a clean slate here. What you notice if you're looking at this from front to back is that those hydrogens are eclipsed. Okay? They are fixed in that position. There's no room in this ring to allow any real rotation about any of the carbon-carbon bonds, because it's only 3 atoms defining one plane. Those 3 carbons have to be on a single plane, right? So this carbon-hydrogen bond and this carbon-hydrogen bond are completely eclipsed. So that's why cyclopropane has such high extra energy to the molecule, because there's no way to alleviate or release any of that torsional strain by moving or rotating. So it's stuck in that one conformation. It's the only conformation available to it. All right? Well, if you add one more carbon to that ring, let's take a look at the cyclobutane ring. What do you notice about this structure that was absent in the cyclopropane ring? I mean, just looking at this, what's different? Yeah, we've added one more carbon. We have opened up that ring a little bit, and now, although there's not a lot of room to move, there's a little bit of puckering of this ring. It's not completely flat. Okay? That pucker allows a little bit of release or easing of that torsional strain. And if you look down this bond, in this view, I'm looking here from a carbon in front to a carbon in back, you can see that these hydrogens now are no longer 0 degrees apart when you look at that from front to back. They're slightly twisted away from each other. And the ring is not completely flat. So in this one, it puckers up a little. And you can see that down, that pucker in that ring. That helps to release a little bit of that torsional strain. Not a lot, because they're still pretty close to each other. But certainly it's a little better than in cyclopropane, right? Hopefully. That's why the ring strain energy on that graph I showed you of relative heats of combustion for the cycloalkanes, the cyclobutane was a little bit less than cyclopropane. Yeah, that's shown right there. Cyclopropane, highest. Cyclobutane, a little bit less. Okay. Now, notice there's a big drop-off in this when you go to the cyclopentane and the cyclohexane. Okay, so clearly the more we open up this ring, the more we are relieving some of those things. I didn't mention also on cyclobutane, I guess I should mention that. If you think about cyclobutane, what should be the bond angle? It's a square, right? So what should be the bond angle? 90 degrees. If it were flat, because it can pucker just a little bit, it's probably a little bit bigger than 90 degrees. I don't know the exact number, but it is a little bigger than 90 degrees. That's another reason why it's not quite as strained in terms of the angle as cyclopropane is as well. Okay, but let's take a look at the 5-membered ring. Now you can see there's a significant difference in that structure in which the bonds are able to avoid more of the torsional strain and the angle strain, because once you can start bending the ring out of a single plane, those bond angles can open up to a more favorable position. Now, with a 5-membered ring, if you look down one of the carbon-carbon bonds where that puckers, you'll see that we have achieved almost, not quite, but almost a staggered position here, right? That's not 60 degrees, but it's getting closer to being halfway in between. One of the things about the cyclopentane is that that's true for the bond here where it's puckered. But if you were to look down this bond, for example, you'll see that those are still pretty close. If you're to think about that angle, right? So, although cyclopentane can pucker, it can move one carbon up. It's more like an envelope with an envelope flap. So that can pucker, and now there's a little bit more room for the cyclopentane to wiggle a little bit. So this can actually come down, and this one can go up, and that one can come down, and that one can go up. And so the overall energy is an average of all of those slight motions of the molecule. So each position at some point has that torsional strain being relieved. Just like in butane, when we looked at all the rotations, we're not fixing them all because what you get overall for the energy of the molecule is an average of all of those conformations energy. Okay, so in cyclopentane, there's still some ring strain because the angles are not quite opened up to 109, and there's still a little bit of torsional strain between the hydrogens on one carbon to a hydrogen on the next. When we get to the six-membered ring, that's when everything aligns in just the right way to relieve all the torsional strain and all the angle strain. So the six-membered ring, in its most favorable conformation, adopts this structure, often referred to as a chair conformation because it looks kind of like a chair. What's the word? A chaise lounge. Your book uses that word. A chaise lounge. You know, these chairs with a back and a footrest. So this looks like a chair structure, and we refer to that as the chair conformation. There are other conformations cyclohexane can adopt, and we'll take a close look at those. They are higher in energy because of increasing in some of these other strains. But if you look at the structure in this particular conformation, what do you notice about this structure? There's enough room that all bond angles can be opened up to about 109 degrees. Okay, and if you look, if you envision, let's see, how did I picture that? Looking down this bond, there's your little eyeball, looking down that bond. And if you do that, if you're looking at that direction of the molecule, you're also looking down that bond because it happens to be parallel. And that's the picture you see on the right. And we can draw a very nice Newman projection for this molecule. Actually, a kind of a double Newman projection. So each side, you see a carbon overlapping from the front and the back. Can you visualize that? And if you look at that, look at the angles from the front to the back, okay? There's our Newman projection, and it's perfectly staggered right in the middle. That's why there is no additional torsional strain because the six-membered ring can adopt that best position to have it staggered. All right? And you can draw this sort of double Newman projection, and oftentimes we represent a cyclohexane like that in this sort of double Newman projection. So you can visualize and see the relationship between groups on one side, the front carbon versus the back carbon. So that's 60 degrees. This is 60 degrees from the front to back. Okay? Now, there are some other aspects of this structure that I need to point out. And this picture shows us that pretty well. So if you take a look at this picture, I've color-coded the hydrogens. Some of these hydrogens are pink, and some of these hydrogens I've color-coded as blue. Because a six-membered ring puts hydrogens in different kinds of environments. So not every hydrogen on the carbon is the same. So you notice, if we're looking at the molecule like this structure on the right from that perspective, you see that there are bonds which go straight up, and there are bonds going straight down. Okay, we refer to these as the axial positions on a cyclohexane. The blue ones are sort of pointing out from the ring. So all of these blue bonds, this one's coming straight towards you, that one's going straight back. They're all pointing away from the ring. And they are in the, if you envision that as a circle, it's in the equator of the ring. So these are referred to as equatorial positions or equatorial hydrogens. Okay, and they are different because they have different steric environments, and we'll see that a little bit more carefully. If you look at this molecule in the next slide from the top view, so all I've done is taken that structure and rotate it so you're looking down on top of the ring. You can see a little bit more clearly the differences between the hydrogens which are axial and the hydrogens which are equatorial. Okay, notice the blue ones are all pointing out away from the ring, and the pink hydrogens are going up towards you or down away from you. Okay, one thing I want to point out about this ring that you should keep in mind, and some good rules of thumb to remember. As you go around the ring from one carbon to the next, the position of the hydrogen alternates. So the hydrogen which is on the top, or the top side of the ring, here, if we start here, this one is axial, the next one is equatorial, the next one is axial, the next one is equatorial. That alternates from one carbon to the next. The ones you can't see on the bottom of the ring, right, there's an equatorial hydrogen pointing straight down there. So equatorial on this carbon is up. If you go to the next carbon, the equatorial position is down. So if we're looking at a particular side of the ring, okay, up and down alternates. Axial alternates from up to down to up to down. And the equatorial position will alternate from down to up to down to up. Okay, and if you can keep that straight, you'll be good going forward. So that's actually a good representation of the differences between those axial and equatorial. We draw these cyclohexane conformations in very specific ways, and when we draw them using single lines as bonds, there are some assumptions we make when we try to visualize that, and that's not always apparent if you're not used to seeing how we draw cyclohexane conformations. So I want to talk a little bit about how to draw them and how to draw that chair conformation. Okay, so you noticed in that structure we had something like, I'll just draw from the side. Okay, kind of a chair. Those are the 6 carbons. And I want to point out that when we draw this, we are assuming that the bonds that are lower on this are coming out closer to you. So we don't often draw them as bold, but if I were to draw these as bold lines, okay, that gives the better, terrible. That gives you a better perspective. And one of the problems with seeing these for the first time is if I just draw it like this, hopefully in a better chair, you don't often think that this is coming towards you. You might think this one is coming towards you, but it's not. We assume that the bottom bonds are always coming towards us. Okay? So I want you to be aware of that, and don't make the mistake that the top bonds are closer, because they're always farther apart. Because we're always trying to look at a side-on perspective of the chair conformation. Okay? I'm going to erase this and draw it one more time. Okay? Another thing I want to point out is that if you draw the chair structure properly, you notice that there are certain bonds that are parallel with each other. each of the two bonds, actually there are 3 pairs of parallel sets of 2 bonds, and I want to point them out. So one of them, if you look at it, are these middle bonds here. I'm just going to color them blue. Notice I've drawn those absolutely parallel with each other. That is the best form for the chair. But if you take a look at, let's just use red here. If I take a look at this bond, what bond is that parallel with? Yeah, it's parallel with this bond. Okay? And the last 2 bonds here are also parallel with each other. So if I make this one green, that's parallel with that one. Although they're not right next to each other. But I want you to realize that they are going exactly at the same angle on the paper. And if you do that and draw these consistently that way, it makes it so much easier to put things onto here properly. So you'll notice that it's always bonds that are opposite each other on the ring that are parallel. So these bonds that are exactly opposite on the ring are parallel. These red ones, although it might not be that easy to see, these are exactly across from each other in the ring. And the green ones, from this perspective, is not that easy to see, but these are actually exactly opposite of each other on that ring. Okay? So, could you draw that particular structure in that way? You should hopefully at some point be able to do that with some ease. Okay, I'm going to draw a chair one more time. Actually, I should show you how we sometimes do this. So one way to do this right is to just start on sort of the top left and draw a bond slightly angled down. And what I'm doing is drawing the 2 middle bonds. And if you go straight down, I'm just going to show you visually where I'm going, straight down and draw another bond. Okay? Those are you could always start with those 2 parallel lines. And then you simply connect them here and connect them here. And if you have the right angles, all the bonds should be the right ones that are parallel with each other. Okay, I'm going to erase my little guideline there. So that's a good way to do this. Now, when you want to represent the positions on the ring, the hydrogens I haven't drawn here, from this chair structure, we always draw the axial hydrogens at each corner of this ring as straight up or straight down. So here's an axial hydrogen. Here's an axial hydrogen. Notice I drew this on top because this side is coming closer to us. So here's an axial hydrogen. So where those bonds join and point upwards, there's an axial hydrogen going straight up. So it's pretty easy that way. The chair structure drawn this way leads you to that. And where those bonds connect and are pointing down, there's an axial hydrogen pointing straight down. And this one is behind. Okay, so those are the 6 axial hydrogens. I know I've done it right because they alternate up, down as I go around the ring from one carbon to the next. You usually have 3 on the top side and 3 on the bottom side, all alternating. Okay, what about the equatorial hydrogens? How would we draw that on here? Let's see if I get a different color. Okay. The equatorial hydrogens are all going out from the ring, and those also now, since we're talking about bonds that are going out away from the ring, each of those bonds also are in the same position in terms of angle or parallel with one of the CC bonds. So if I draw from this position here, the equatorial position will be there. Okay? What bond is that parallel with? Yeah, notice these 2 parallel bonds that I'll highlight right here. this bond is parallel with those two. Okay. Likewise, on the other end of the molecule, notice I draw that slightly up to represent the equatorial position. That bond is also parallel with those two middle lines. Okay? Let me color code the parallel lines in the ring again. So this one is going to be parallel with this one. And what did I use? Green. This one is going to be parallel with this one. Okay, so when you draw the other equatorial positions, then you put also parallel lines. So from this one, that's coming out. So perspective-wise, that hydrogen I just drew is coming out towards you. And I do it green because it's parallel with those green lines. There's one more carbon with a green hydrogen equatorial that's parallel with the green lines. Which carbon would that be? Notice the green line that I drew for this hydrogen is opposite of another green CC bond. So if you take a look at the other green CC bond, it's the equatorial hydrogen that would be in the same parallel line would be opposite that. That's going back away from us, from the perspective of this drawing. Okay? And finally, there's two equatorial hydrogens we haven't put in. They're going to be parallel with the red line, so one of them is going to be here, and one will be here. That's the proper way to represent and draw that. And hopefully by taking time to go through this, it'll help you to visualize and see the different positions and how they relate to each other. Now it is so much easier to take a three-dimensional model and hold it in your hand and really look at it. Again, if you have difficulty seeing the perspective in your head, I encourage you to get those models and do that. Okay. I don't expect you to be able to draw those chairs just like that right off the bat, but I would encourage you to practice drawing them because you may need to do it at some point on the test or something, or know the different positions. Okay, one aspect about a cyclohexane is that it is able to move. Those bonds can move and rotate a little bit. And so this conformation, although this one is the lowest energy one, it can shift around and it can move. So if you imagine this angle is open up just enough that you could get rotation around these bonds and shift this carbon upwards. All right, if I do that, I'm going to erase this and draw it again. If I do that, when we start my typical chair here, oops, that one's not very straight. Okay. Those two parallel lines, and this one goes up, and now this one has shifted up. So let me just put I'm just going to dot in here what the old conformation was. Okay. That has now moved up because we've been able to rotate these bonds slightly and swing that upwards. Okay, the molecule has the ability to make this motion because it's not so strained that it's stuck. It can't rotate any further than that, but it can certainly get to there. What have we done to this picture now in terms of the energy of the bonds? This molecule, and I should have brought some more perspectives here. This is a conformation which we refer to as a boat conformation because it looks like a boat, right? Oftentimes I draw it a little bit better, starting with two horizontal lines. So it's sometimes a little bit easier to draw it like this. Wow, my drawings are terrible. My bonds should all be the same length. Hard to draw on the iPad. The boat conformation, and again, we are assuming that what is closest to what is lower on here is coming up closer to us. All right? Now, if you take a look at this and where the hydrogen bonds might move, you can see that this molecule in this conformation has some more energy strain in it. So I'm just going to draw some of these. In this boat conformation, I didn't draw the hydrogens on the back, but you can see from this. Now, these bonds, if you were to visualize down that carbon-carbon bond, what would those bonds look like? What would those hydrogens, the angle from this hydrogen on front and this hydrogen on front? They're eclipsing now, right? So what have we done? We've increased the torsional strain in this particular conformation. These two bonds that are going down here, those are eclipsing. The other thing is that we have now put hydrogens here closer together. That's not so much of a problem if it's something small like a hydrogen, but if it's bigger, if it's a bigger group, that's going to be a severe interaction and start introducing steric interactions. Okay, so if you take a look at this, I should have drawn it side by side, sorry, I have to erase this. But if you take a look at this molecule now and you visualize down those two carbon-carbon bonds, you're going to see a little different picture than we did with the Newman projection for the chair. And so I'm going to draw two Newman projections here, and the bond in front and the bond in back. And this is the boat conformation. Oops, that was wrong. This is the boat conformation now looking at those bonds. So you can see that those are eclipsed. Coming out here is a hydrogen and going back is a hydrogen and also on that back carbon. So you can see now that these are eclipsing, and you would expect this conformation to be a higher energy conformation, right? So it's true, the boat conformation of cyclohexane is higher in energy. It prefers to exist in the chair conformation. But if you can bend one end up, you can bend the other end down at the same time. So one of the aspects of a cyclohexane ring is that if you, I'm going to use my body here, if you have one chair conformation, you can flip to the other chair conformation. You can flip up and down at the same time. In the process of doing that, what happens with every position on the carbon, everything that was axial becomes equatorial, and everything that was in an equatorial orientation becomes axial. So in a flip of one chair to another, you've switched the positions of all the axials and equatorials. Because the carbon has to rotate as it's making all those motions. And I should have a movie drawing which should show you a little bit more details of that. Yeah, so you can see the motions of the cyclohexane molecule on here and what happens. Okay, so notice there's a chair and there's a chair. You can see it from the side. That one's a little harder to see. But as the molecule moves, take a look at this hydrogen, for example. And here it's axial, and as it flips to the other chair, it becomes equatorial, pointing out. And if you look at a position on any part of this, okay, here, for example, this is axial, and as it flips, it becomes equatorial. Okay, that's the motions that are available for a cyclohexane. Okay, and cyclohexanes freely are making these motions at room temperature. And if you really look at the conformations as it's going from one chair conformation to another and analyze those all the way along, what you see is as the molecule starts to rotate one end up, it gets to a point which is a high energy point referred to as a half chair. And then as that swings up further, you get to kind of a twist boat type of situation, and then to this boat. Notice, though, the relationship of a boat conformation to a chair conformation is significantly higher in energy. Okay. And then it can go back the other way. So you can go from the boat and flip the other end down now, and you go up to this point, and then down to the chair as that end goes all the way down. Again, if you go from, excuse me, if you go from one chair conformation and flip to the other chair conformation, I reiterate, all of the positions that were axial before are now equatorial, and all the positions that were equatorial before are now axial. That's an important key concept to keep in mind whenever you're thinking about chair conformations. Okay? So I want you to keep that in mind as we continue talking about some of the interactions that happen when we start to substitute these molecules. Because once you start to put additional substituents onto a cyclohexane ring, those axial and equatorial positions become very important. And then one chair conformation might not be the same energy as the other flipped one. And that's the case here. If you take methyl cyclohexane, so one of the positions now has a hydrogen exchange for a methyl group. That methyl group, depending on which chair you're in, can be in an axial position or in an equatorial position. Okay? The axial position, another thing to keep in mind always, the axial positions are always more crowded. So once you start to get groups on there which are larger than hydrogen, we have steric strain introduced to that molecule. And that's because around the ring, alternating every other carbon, there are also two other axial positions on that ring, and they each have a close relationship. They come closer together than if they're out in the in the equator of the ring in an equatorial position. Okay? So in this case, I've drawn an equilibrium arrow to represent this conformational change. If you bend that down and bend that up, now this axial position becomes equatorial, and there's much more space for that methyl group to be in. It's open space. So that's a lower energy conformation. So if you were to take, say, look at the population of these two different conformations at room temperature, you would see that you'd have more of this conformation than that conformation present in that sample. And the difference in energy for one methyl group is about 1.8 kilocalories per mole. So this is lower in energy, or more stable, by 1.8 kilocalories per mole. So what that means is that the steric interaction between the methyl group and the hydrogen, if you look at one side of this ring, now methyl group, hydrogen, hydrogen, okay? Each of these interactions will be referred to as a 1,3 diaxial interaction because they're 3 carbons apart. A 1,3 diaxial interaction between a hydrogen and methyl, each one of those would be about 0.9 kilocalories per mole, adding to the steric strain. And we get that because we know that if we take that methyl group out of that position, it's lower in energy by 1.8, or the addition of those 2 diaxial interactions. So on any side of the ring, you also always have 3 axial positions, and so you always have this kind of situation where these can bump into each other. Okay, and if you take a look at actually the models for this, you can get some better perspective on how much that steric interaction is really there. So here's the methyl group, and notice if I draw out all the bonds of the methyl group, it's suitably large, okay, and coming close. And you can see here in the space-filling model how close that methyl group is coming to those hydrogens. So this is a side view looking at the chair structure, and on the right you see the top-down view looking at the top. So you can see this hydrogen and these axial positions. So that methyl group coming close, which is really apparent in that space-filling model. Okay? So you see how close they are in this position with an axial. If that molecule now flips to put that methyl group in the equatorial position, you see that there's a lot of space for it. Okay? That methyl group is not bumping into anything. Here's the side view, and here's the top-down view, and you can see plenty of room for that CH3. It's not bumping into anything else. Okay? So clearly, the equatorial positions are less sterically crowded. Here's a visualization also of how that flips. Again, it's the same chair structure flip. Methyl axial, as it flips, the methyl goes equatorial. Okay. Flips down, equatorial. Now, for a typical molecule, about 1.8 kilocalories per mole isn't that much energy. Both of these conformations are existing at room temperature. But as you get more and more crowded, then those energies get more and more difficult to overcome. And sometimes if the groups are big enough, you only have one of the conformations possible at room temperature. There's not enough energy to flip it to the higher energy state. One more thing I want to talk about with regards to ring structures is that if we have more than one group on the ring, now we have another situation where we have different kinds of isomers for a molecule. And it's different than the types of isomers we talked about before. We talked about isomers of molecules which are different in how their atoms are connected together, right? They're connected differently. They have a different skeleton. So butane versus 2-methylpropane, or isobutane. Those are constitutional isomers. In the case of rings, one of the problems with a ring is that if it's tied together, there's no complete free rotation, 360 degrees, about any of the carbon-carbon bonds of the ring. So every ring has two different sides. There's if you draw it looking at the side, there's a top side and a bottom side. So if you have two groups on a ring, and you put them both on one side, let's say you have one on one carbon, one on another carbon, and they're both pointing up. But you take one and you just switch it, exchange it for the other hydrogen there, and point it down. Those molecules aren't the same. But we haven't changed which atoms are connected to which atoms. They've just changed in their three-dimensional arrangement. This is what we refer to as stereoisomers. Isomers which have all the same number and kind of atoms. All the atoms are connected to the same atoms, but they're different in their three-dimensional arrangement and stuck there. Okay, and because the ring is restricted, it's stuck there. So next time we're going to talk much more in detail about cis and trans isomers, which is what we refer to for these types of structures. And we'll look at how the cyclohexane conformations are affected by those cis and trans stereoisomers.